Hey guys, it's day 2 of alternating series. We're still in the simple pieces of series. An alternating series, we're going to start today, however, with remainders, which we haven't been talking about. An alternating series that converges also has an error which equals the sum minus the partial sum, or the absolute value of that. So the remainder is always going to be I forget my words. The remainder will always be less. Oh my gosh, you guys, I gotta re-record this. I can't. I don't know how. So you're just gonna have to suck it up and listen to that crap. Sorry about that. The error will always be smaller than the first omitted term. So we're looking at a particular series and we're going to approximate the sum using its first 4 terms. So obviously we first find our first 4 terms, then we go ahead and find the sums. So there we go. There are our first 4 sums. And I'm going to go ahead and find the next term because I'm going to need it for B. Because we have an alternating series and that alternating series converges, then the error will be less than the absolute value of the first truncated term. The first truncated term is 1 over 120. So the error, the absolute value of R sub n, is less than 120, which is less than 1/100th. So we have proven B. Remembering that our remainder can actually also be written as the sum of the series minus the partial sum, the absolute value of that. And in this case, we're actually looking at the difference between the sum of the series and the partial sum of the first 4 terms. We can set that error less than 120 and solve for x, our actual sum, and figure out what our actual sum is between. Oh shit, I forgot to press pause, y'all. Damn it. Okay, well anyway. Yeah, your sum is somewhere between 0.617 and 0.633, rounding to the 3rd decimal. So therefore, S cannot be 7/10. I know you feel this. I included this just for you. Here all we need to do is go out in our terms so that we have a term whose absolute value is less than 1/1000th. So just carry out your terms, figure out the sums of the others, and you're good to go. Guess what? You don't even need to figure out the sums. I don't know what I was thinking. And there we go. We only need 1, 2, 3, 4, 5 terms to be able to see that our estimate differs from the actual sum by less than 1/1000th. Now you need to justify your answer. I need to, I guess. I'm the one doing the work. Okay, 5 terms are needed because we have an alternating series which converges by the alternating series test. I put that particular proof in parentheses here so that you could see it, just in case you forgot what it means to converge by the alternating series test. And then you see that your error, when you go out to the fourth sum, must be less than the absolute value of 1/1296, and 1/1296 is less than 1/1000th. So 5 terms are needed. So there's the first half of your notes, and now for a fun meme. Don't forget your number 2 pencils for the AP Calculus test. So far, you have learned about geometric series, the P-series test, the harmonic series, the direct comparison test, the limit comparison test, alternating series, and telescoping series. If none of those tests work, you can use the ratio test. If that doesn't work, you can use the root test. With practice, you will be able to figure out which test to use when. The ratio test states that a series converges if the next term divided by the current term, the limit as n approaches infinity of the next term divided by the current term is less than 1, and it diverges if the limit as n approaches infinity of the next term divided by the current term is greater than 1. If the limit as n approaches infinity of the absolute value of the next term divided by the current term actually equals 1, then the ratio test is inconclusive, so another test would need to be used. On this first example, we take the next term divided by, the limit as n approaches infinity of the absolute value of the next term divided by the current term, and we get a limit of 0, which is less than 1. And just to review some algebra in here, this 2 to the n cancels with this 2 to the n, and you're left with just 2 to the 1. I'm sorry, my pen's not working properly. Give me a second here. 2 to the 1, and that n plus 1 factorial can be written n plus 1 times n factorial, which does allow you to cancel those n factorials. Because that limit is less than 1, you can say that the original series converges by the ratio test. On this second one, we look at the limit as n approaches infinity of the absolute value of the next term divided by the current term. And we see that that limit is 3/2, which is bigger than 1. Therefore, the series diverges by the ratio test. Now, I want to talk about a few things. One thing that I did here was that I used dividing fractions, y ask y, just flip the last and multiply. That should be fairly apparent to most of you. What might not be apparent is the fact that I changed this 3 to the n plus 2 into 3 to the n plus 1 times, oh crap, my pen's not working, times 3. And this 2 to the n plus 1 can be written 2 to the n times 2, which allows you to cancel these and those. That's old algebra rules. This series diverges by the ratio test, and you are done. On example C, you see very quickly that your numerator is definitely bigger than your denominator. That is definitely bigger than 0, and the series diverges by the ratio test. The root test works similarly, where the series converges if the limit of the absolute value of the nth root of a sub n is less than 1, it converges, and it diverges if the limit as n approaches infinity of the nth root of a sub n is greater than 1. But if the limit as n approaches infinity of the nth root of a sub n equals 1, the root test is inconclusive, so another test would need to be used. Okay, so I did a bunch of math in my head in this first line, and I apologize. So it probably looks pretty confusing. So what you might want to do is ignore this whole part, because this first piece right here simplified is this second piece right here. That limit as n approaches infinity of e squared over n is less than 1. Well, how did I get from that first step to the second step? I was taking the nth root of those nth powers. I realized after I did that that wasn't altogether obvious. So you can simply say, once you've done that work and shown that work, that the series converges by the root test. And when we take the nth root of the next series, we see that that limit of that nth, oh my gosh, I'm really tired. The nth root of that, gosh darn it. Anyway, you know what I'm trying to say, is 3/2, which is bigger than 1. Therefore, that series diverges by the nth root test. Doo-doo. All done. No more neat little meme things.